Howdy, Huskies. We're going to go ahead and get started with day 5 here today. And in day 5, we're going to talk about tangents of the circles. We're going to throw in secants for a hot second, but it really is all about just about the tangents for us today. So, ladies and gentlemen, our tangent is going to be a segment, line, array, because it could be any of those things, even though we have a ray drawn that intersects with a circle, because clearly we're in our circle unit, and this is the kicker, exactly once. So that exactly once is that actually a very important concept right there, because if it hits more than once, that is not a tangent. So this comes from, say you're having a conversation, you hear this a lot. If you're having a conversation and then you get to about this point in your conversation and then it goes in a completely different direction and you're like, how did we even get to this conversation? We were talking about Spider-Man and now we're talking about food. I'm confused. And so the way that happens is that at one point it made sense, which is this point of tangency right there, and then it left. So that intersection, and we're going to talk about this here in just a second, is known as the point of tangency. I'll just say point of tan for now. So then, ladies and gents, if it hits twice, as we see in this next diagram, right here and right here, then that is a secant. So I'm just going to say hits a circle twice so we can see the difference. We're not going to be so into secants. We're really going to focus on tangents here today, but we'll throw that out there. So in this next example here, we're just looking at this diagram that we have right there and saying, what's going on? Let's talk about things about different pieces that we've talked about this unit. So let's review. So the center is obviously going to be the middle. And what's going to be important is that it's also going to be a point, because the point of tangency is going to be on the circle and it's a point. So it's important to know that the center is going to be inside and that the point of tangency is going to be on the outside, on the circle. And the rest of these are all going to be segments. So a chord is going to be inside, and it's going to go end to end. It doesn't always have to go through the center, but it can. A diameter is going to be inside, end to end, but it has to go through the center. So the center is included. A radius is going to be from the center to a point on the circle. And then we get to this concept of our tangents, and we have internal and we have external. So external is going to be basically the outside, and then the internal is going to be the inside. But what we're going to use it today is really, we're going to say it's going to be in between. And these are both going to hit once. So I'm just going to put once right there. And then last but not least, we have our secant, and that's going to go ahead and hit twice. So since I went ahead and did this kind of review for you, why don't you hit pause and give this a shot, and then come on back and see how well you did. Welcome back, or you just didn't hit pause, one of the two. So we're going to have F. So if we take a look at F, F is a point, and it's on the circle. So it really can only be one thing. It's going to be our point of tangency. So there we go. And then we have FE. I'm going to go ahead and put some arrow marks on here. It's a little bit tough to see some of those because it's important, because secants and tangents go outside the circle, but diameters, chords, and radii have to stay inside. So FE with the arrows implies that it can leave the circle. So FE, I'll go ahead and do this one here in orange. It's going to be this segment right there. Well, clearly, it's going to hit both circles once here and once here. So it's going to be tangent to both circles. But it goes in between here, both circles. So we're going to call this the common internal tangent. And then HG, we'll do HG here in green. Now notice it doesn't have arrows, so it has to stop. So HG is going to go from the center to a point on it. So this is clearly going to be a radius. So DB is going to be the same situation. It's going to stop inside of the circle. So let's go ahead and take a look at this. So if I just look at dB without any arrows, it is just that piece. But if I do dB with arrows, then that becomes a secant because it can go ahead and keep on going this way and then this way. But since it doesn't have the arrows, we're looking at just the pink part of that. So this is going to go ahead and become a chord. And it's a chord because it doesn't go through the center. So C is this point right here. It's in the middle, so clearly this is going to be the center. Easy enough. So BE is going to go ahead. We'll do this one here and this purple here. So BE is this one right here. So I'm going to erase some of these other ones just so we can focus. So BE, we can see that it's, once again, it's inside the circle, okay? So it can't be a secant, it can't be a tangent, but this is actually can be, the best word would be the diameter, but technically it also could be a chord, okay? But a diameter is definitely the best. It could be a chord too, because every diameter is also a chord. All right, dB here, we'll do this dB. It's got arrows, so it's going to be all the way through. And clearly that's going to hit twice, so we're going to call that a secant. And last, but it's going to be AG. And we'll do this AG here in orange here. AG is going to be this one right here. It's clearly tangent at one spot here, one spot there, and on the outside, so this is a common external tangent. So that was a good exercise just to make sure that we were all good with the vocabulary of these segments that we've been talking about. But let's really get into kind of what we're talking about today. So we're going to look at two main theorems. The first one's a perpendicular tangent theorem that says if a ray or, so I should say, we should do all three. So a ray, segment, or line is tangent to a circle, then, and then this is the important part, so I'm going to change my colors here, then it is perpendicular to a radius / diameter. So if this is my center C, then it becomes perpendicular right there. So if it's tangent at P, then we're going to say it's perpendicular. Now, why we care is that many times that means that we're going to go ahead and look right here at a right triangle. So perpendicular, this lovely shape right here, is going to also mean a squared plus b squared equals c squared. So let's keep that fresh and ready to go because, oh wait, there it is. So it's going to say, is AB tangent to C? So if AB is tangent to C, then it means it has to be perpendicular to C, which means there needs to be a right angle at C, which then means that there needs to be a right triangle, which means a squared plus b squared equals c squared. So moral of the story is perpendicular, a squared, b squared, c squared. So this is going to be my point of tangency. We'll say it's point of tan again. So we're going to say, is this right here going to be a right angle? So if we zoom in here, this is a triangle that we can see. And so we'll go ahead and call this my A, my B, and then this whole thing is going to be my C. So if I were to draw that real quick, it would look like 5, 12, and then 13. Because 5 plus 8 would be 13. So basically, if it's a yes, that means that a squared plus b squared equals c squared works. If it's a no, then a squared plus b squared does not equal c squared. So that's basically what we're trying to figure out. So let's go ahead and give this a shot. So it doesn't matter which one is a and b. So I always go smallest is a, and then b, because the largest has to be c. So a squared plus b squared is equal to c squared. So 5 squared plus 12 squared is equal to 13 squared. So 25, 144 is equal to 169. So when I add up the left side, that's 169. That equals 169, so that works. So what that means is that it's true, so this is a yes. So yes, AB is yes, AB is a tangent. Because that's what we were trying to figure out this whole time. Okay. All right, let's look at this next one. So here's my point of tangency. So 90-degree box right there. So I'll go A, B, C. So same concept, A squared plus B squared equals C squared. So 8 squared plus 16 squared is equal to 20 squared. So 64 plus 256 is equal to 400. Now, clearly, this is not going to work. Because when we add those, I get 300 here. Excuse me, 310. We'll fix that. 320 even. But that still does not equal 400. So this is a no. So what that means is that AB is not a tangent. Now, some of you are like, well, wait, Mr. N, it doesn't look like the tangent. Look at the diagram. And I think that's just a bad diagram. But the idea is that we do the Pythagorean theorem to double check. So this is one of the things you're going to need to know about tangents, okay, is that 90 degrees right triangle goodness. The next one is the intersecting tangents thing. So if two tangents are tangent to the same circle, that's important, and have a common point, then they are congruent. So clearly this is going to be my same circle that both of those tangents are going to go to, and this is my common point. If that is the common point, then that means that this piece and this piece are the same. So what I like to think of this as is I remember this as party hat. Because if I make this a smiley face, and then this my party hat, like the little like foo-foo thing is up here, a little like bubbles, make it a rainbow, then the hat needs to be the same. So I try to remember that the shape looks like a party hat, and then you're good to go. So number 11, we have a party hat situation here. So look at this. Even if I draw it in, that C becomes the nose. That's pretty perfect right there. So this part is going to be congruent to this part right here. So 7x minus 2 is going to be equal to 3x plus 8. So that's going to go ahead, and if I move that over, so minus 3x. And so I'm going to get 4x minus 2 is equal to 8. Go ahead and add 2 to both sides, and I get 4x is equal to 10. Divide both sides by 4. And so I'm going to get 5 over 2, or 2.5. Not a horrible decimal. Definitely doable. Definitely workable. All righty, ladies and gents, let's go to the next one here. So next one, we have a party hat again. Party hat, woo! Living the high life here in geometry. So this part, this 10x, is going to be equal to this part here, which is going to be the 5x plus 25. So when I move that over, I get minus 5x. Minus 5x, and I get 5x is equal to 25. So when I divide both sides here by 5, we're going to get x is equal to 5. A much better number here. All right, why don't you try number 13? Be careful on this one. You're going to go ahead and get a decimal. So I just want to give you a heads up, or a fraction. All right, welcome back to the party hat. So this part and this part were the same. So 12x is equal to 4. And then you're going to divide both sides by 12, and I'm going to get 4 divided by 12, which is really 1/3. And that's our answer right there. So be careful, always with that algebra. All righty. We got one last one here. We have this little circle here. This is a very common problem that you see on your final. They love to ask this question a lot. So that's why we're putting it on our notes, so we're good to this. So it says, a freeway runs tangent to a circular lake. So clearly, if it's going to be tangent to the lake, I only see one tangent. So since I have one tangent, it's not going to be a party hat situation. This is going to be, or like, okay, if it's at this part at A, then that means we're going to have some 90-degree action. So it says the distance between point B and the center of the circle is 100. So from here to here, this whole thing is 100. And then it says the the distance of A to B is 80. So that's this part right here. And what is the diameter? Now, most of you guys are like, well, this is the diameter, so what am I supposed to do? I don't know. Well, what they want you to do here is remember that this is radius. That's your radius r. From the center to a point on the circle. And so if I find out what the radius is, I just double it. So we got a little lovely 90-degree box here because it's perpendicular, because of that one tangent. So we're going to do r squared plus 80 squared is equal to 100 squared. So we're going to get r squared plus 6400 is equal to 10,000 here, I believe. And then when I move that 6,400 to the other side, I'm going to get r squared is equal to 3,600. And then when we take the square root of both sides, we get r is equal to 60. So that means here the radius is 60. Well, I want the diameter here. So we're going to remember that the diameter is twice the radius. So 2 times 60 means it's 120 miles, which seems like a giant lake, but there you go. Alrighty, friends, hopefully this was helpful, and we'll see you next time. Take care.